Hello everyone, welcome back to our NDT training session. I am Muthulakshmi Kanagaraj, Quality Expert, ASNT Level 3 in 10 Methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. In our previous session, we are discussed into the fundamental techniques and equipment used in magnetic particle testing. Today, we are going to dive deep into a crucial aspect of magnetic testing, that is, understanding the various types of discontinuities found in ferromagnetic materials and how they originate. This knowledge is fundamental for effective magnetic particle testing applications. Our focus today is on discontinuities in ferromagnetic material protection, which we can categorize into three main stages. Let's start our session. So, the three main stages are primary protection and processing, and secondary processing, and service induced. Let's break these down in detail. Primary protection and processing. These discontinuities form early on from the pouring of molten metal to the creation of basic shapes like sheets, bars, pipe, forgings and castings. First, let's understand how ferromagnetic materials like steel are produced. It starts with iron ore, which is melted and alloyed in furnace, then cast into ingots or continuously cast. This initial stage is critical as many inherent defects can form here. First, inherent discontinuities. Inherent discontinuities originate during the initial melting, refining and solidification of steel, meaning they are present before any hot or cold working like rolling, forging even begins. This is inherent. Here are some key types: pipe, non-metallic inclusions and blowholes. First, the pipe. This is central cavity formed due to shrinkage during solidification. So, pipe is central cavity formed due to shrinkage during the solidification. Think of it like a void that forms at the top or center of an ingot or continuously cast shape as the metal cools and shrinks. If this is not properly cut off, it will show up in the semi-finished products. So, these are the primary protection and processings. Then secondary processings. These occur during subsequent manufacturing steps such as forming, machining, welding or heat treatment. Many of these are surface breaking and thus readily detectable by MT. Detectable discontinuities include cracks, seams, laps, laminations, inclusions and lack of fusions. Cracks, generally MPT detects cracks, specifically HAZ, heat affected zone, near welds, it caused by thermal stress, are easily detectable. Next one is crater crack at weld terminations from solidification stresses are widely detected with MT. Next, we take a lack of fusion, where base metal fails to fuse with filler metal in welds, appearing as a void. It is detectable if near the surface. Next one is service induced. These develop during the actual operational use of a component. Overstress cracking and fatigue cracking. First, overstress cracking caused by loads exceeding material strength. Yes, detectable if no visible fracture occurs. Next is fatigue cracking. Initiated by cyclic stress growing over time, especially at stress risers. These are typically surface cracks and are detectable. And the corrosion, deformation or wear, though it can detect fatigue cracks initiated by pitting corrosion. Flux leakage testing detects material loss, which is distinct from MPT detects material loss like corrosion in wire ropes. Deep internal flaws like flakes unless they are near the surface. Next is internal laminations, they do not break the surface. Lack of penetrations in welds, as this is usually an internal defect. Let's go to the next slide. Here I mention some common discontinuity types and origins. Discontinuity types and origins. Cracks, fast cooling of quenched steel. Next, seams arise during processing or form a elongated inclusions. Forging laps, rolled over fins or gouges during forging. Laminations, internal fusion, defects from casting or rolling. These are the common types of discontinuities. So we move the next slide. Protection of ferromagnetic materials. Already we are discussing in the steel mill life cycle. So this session briefly outlines the fundamental process of steel protection. Iron ore is a molten metal and alloyed in furnace. The molten metal is then cast into ingots or continuously cast into various forms. This initial melting and solidification process is where inherent discontinuities begin to form. Intermediate shapes. After casting, the steel is processed into various intermediate shapes, which are then further worked into the final products like bloom, billets, slabs. These are only differs with shape and size. Next, inherent discontinuities. This is a crucial category of discontinuities. Inherent discontinuities originate during the initial melting, refining and solidification of metal or steel. These are present before any hot or cold working. This means they are present before any hot or cold working process such as rolling or forging have begun. Types of inherent discontinuities are pipe. This is a central cavity that forms due to shrinkage during solidification. It is typically found at the top or center of ingots or continuously cast shapes. If this pipe is not fully cropped off, it will appear in semi-finished shapes. Next is non-metallic inclusions. These are particles like oxides or sulfides that result from deoxidizing agents added to molten steel. Finely dispersed inclusions are generally acceptable. However, the large clusters of these inclusions can become stringers after rolling and These stringes may initiate fatigue cracks. Next, free machining alloys intentionally contain inclusions, example lead or sulfur, to improve machinability. While these inclusions will show up as indications during magnetic particle testing, they are not always detrimental to service. Next one is blowholes. These are gas bubbles trapped during the solidification. If blowholes are near the surface and oxidized, they can become seams after rolling. Interior blowholes can form lamination in plates. It flattened during rolling. However, it's important to remember from our discussion that internal laminations are not reliably detectable by MT unless they break the plate edges. Next one is ingot cracks. These cracks are caused by thermal stresses during cooling of the ingot. If these cracks become oxidized or exposed to air, they do not weld shut during rolling and remain as seams in the final product. They are typically removed by grinding or scarfing after empty inspection of billet. Let's move on the next slide. Primary processing discontinuities. These discontinuities are introduced during hot or cold working, or they are inherent defects that persist as ingots or converted into the final shapes like billets, bars, plates, rods or tubing. Let's look at some examples. Seams. These can originate from ingot cracks or form during rolling or drawing processes. They can also result from overfill, which cause folds or laps, or underfill. Underfill means which creates surface grooves. Sometimes die marks from defective dies can also appear as seams. Seams are particularly objectionable in areas subject to cyclic stress because they significantly increase the risk of fatigue crack. Next one is laminations. These form when blowholes or cracks are flattened during rolling. They typically lie parallel to the surface and are only detectable if they break the plate edges. If they are entirely internal, they are not reliably detectable by MT. Next one is cupping. This is caused by uneven flow of material during drawing or extruding, leading to internal ruptures. These are only detectable when they are near the surface and severe. Cooling cracks. These are caused by thermal stresses from uneven cooling after hot rolling. They typically appear as curved longitudinal cracks and are detectable by MT, with deeper cracks producing stronger indications. Next, forging discontinuities. Forging discontinuities are flaws that form during the hot working process where metal is shaped by pressing or hammering between dies. Improper temperatures, strain rates or tool actions are common causes. Here are some types and their MT detectability. First one is flakes. These are internal ruptures, possibly caused by rapid cooling or hydrogen gas release, typically found deep within heavy sections. They are not detectable by MT unless they are near the surface. Next one is forging burst. These are cracks caused by working the material at improper temperatures or rapid cross-section reductions. They can be internal or surface connected and are detectable by MT if they are at or near the surface. Forging laps. These are surface folds formed during deformation. Because they are exposed to air, they become oxidized and do not fuse, remaining us typically shallow and angled defects. They can be difficult to detect but are possible with MT. Flash line tears. These are cracks that occur at the trimming area if the flash is improperly removed. They are reliably detectable with MT. The next is casting discontinuities. Casting discontinuities are flaws that occur during the pouring, solidification and cooling stages of molten metal into molds. Issues like turbulence, temperature gradients or mold geometry contribute to their formation. Common casting discontinuities and their MT detectability. First is cold shut. This happens when partially solidified metal fails to fuse with incoming molten stream. They can be caused by splashing, interrupted pouring, or metal streams meeting from different directions. They may appear as shallow scabs or deep cracks and are detectable especially in surface breaking areas. Next one is hot tears. These are surface cracks formed due to thermal stresses during uneven cooling, often found at abrupt changes in cross section. They are easily detectable with MT. Next, shrinkage cracks caused by volume contraction during solidification. These appear as surface cracks, often similar to hot tears. They are readily visible with MT. Next one is weldment discontinuities. Weldment discontinuities are flaws introduced during the welding process itself due to melting, solidification and improper technique. Welding is very much like a localized casting process. So defects can occur in both the weld metal and the heat affected zone. Here are some examples and their MT detectability. Lack of fusion. This occurs when the base metal fails to fuse with the filler metal, appearing as a void between the weld and the base. It's caused by insufficient heat or poor technique and is detectable if it's near the surface. Next one is lack of penetration. This means an incomplete weld path at the root area. It's usually internal and due to poor joint preparation or insufficient heat and is generally not detected by MT. Next one is has cracks. These are cracks that form in the base metal near the weld bead. It caused by thermal stresses during heating and cooling. They typically run parallel to the weld and are easily detectable. Next one is crater cracks. These are weld bit cracks caused by solidification stresses or rapid cooling at weld terminations. They are common at the end of weld beads and are widely detected with MT. The next slide is manufacturing and fabrication discontinuities. These discontinuities occurs during finishing operations such as machining, heat treating, grinding, straightening or surface finishing. Many of these are surface breaking, making them highly detectable by MT. Common manufacturing discontinuities. Machining tears. These are caused by dragging of metal instead of clean cutting due to dull or improperly shaped tool bits. They are detectable as surface cracks. Heat treating cracks, that means quench crack. These result from rapid or uneven cooling during quenching. They are common at notches, fillets, corners and are detectable especially when at the surface. Straightening cracks. These are caused by overcorrection of distortion in hardened materials and are detectable by MT. Grinding cracks. These originate from surface overheating, poor coolant, wrong grinding wheel or excessive feed. They are often sharp, deep and can be very dangerous. They are detectable by MT. Residual stress cracks. These result from latent internal stresses combined with localized grinding heat and these are detectable by MT. Next one is service induced discontinuities. These discontinuities develop during the operation or use of component. While not all service defects are detectable by MT, certain types of cracks are effectively identified this method. Here are some common service discontinuities and detectability. First one is overstress cracking caused by loads exceeding the material's ultimate strength. Visible surface operation may or may not occur. These are detectability by MT if there is no visible fracture. Next one is fatigue cracking, initiated by cyclic stress even below the yield strength. These cracks grow over time, especially at stress concentrators. These are typically surface cracks and are detectable by MT. Stress corrosion cracking, caused by sustained stress in a corrosive environment, leading to brittle cracks. These are detectable with MT. Next one is fatigue cracks from pitting. When corrosion pits act as a stress concentrators leading to brittle cracks, they are detectable with MT. Next one is surface corrosion or pitting. It's important to note what MT does not reliably detect in the service. General surface rust, scale or pits from corrosion are not directly detectable by MT, only indirectly if they lead to fatigue cracks. Deformation or wear. Mechanical damage or wear from service is not detectable by MT. However, flux leakage testing can detect material loss such as corrosion in wire ropes. Understanding the origin, characteristics and detectability of these discontinuities is paramount for any NDT professional performing magnetic particle testing. Knowing what you are looking for and where it might come from significantly improves the accuracy and effectiveness of your inspections. I will prepare some questions for this session. Comment your answers in the comment box. I hope this concept is now clear to everyone. If you have any further clarification, please drop them in comment box. Thank you.